Okay, we're going to look at our last static rigid bodies question. So I've got a uniform rod AB, mass 6 kilograms and length 4 meters. So the fact that it's uniform lets me put my 6G, which is the weight of the rod, at a distance of 2 meters from either end. It's smoothly hinged at A, which means there's no resistance to the turning force at A, and it's got a light inextensible string at C, which is my tension there. Now, the string keeps the rod in equilibrium, and we've got our angle of 40 degrees down here. So we've got two of the forces acting on here, but obviously if we just had these two forces, there's no way that it could be in equilibrium. There's already a turning force which would rotate it around where my pen is. So there must be some forces keeping it in equilibrium. Now, the hinge can exert a force in any direction. It can push, it can pull, it can accept torque. The only thing it can't do is provide resistance to turning around itself. So the easiest way to deal with that is to deal with two components of the force at A. We're going to have a vertical component of the force at A, and we might call that A vertical. And we're going to have a horizontal component of the force at A, which we'll call A horizontal. Now, don't worry too much about whether you put those to the left or to the right. If you get the wrong direction, you'll just find it comes out as negative in the end, so it shouldn't cause you a significant problem. So, absolutely as before, we're going to start by taking moments around the pivot point, which is moments around A. So the moment of the weight of the 6G force should be fairly easy for us to calculate. It's just going to be 6G times 2, because that's already a perpendicular distance. So I've got 6G times by 2 is equal to T times the perpendicular distance. Now let's just extend this out so that we can see the perpendicular distance. So here we know that we must be operating at a right angle, and I'm trying to find this distance x. Well, I've got a hypotenuse here of 3 meters. I've got an opposite of x. I've got an angle of 40. So I know that I'm going to have 3 sine 40. So I know that for this to be in equilibrium, the clockwise turning force is going to be equal to the anti-clockwise turning force, which is T times 3 sine 40. Simplifying that, I get T equals 4G over sine 40. And that gives me an answer of 61.0 degrees. I'm going to just store that in my calculator because I'm going 61.0 newtons, and I'm going to need to use that in later part of the question. For the second part of the question, I'm going to need to resolve my forces vertically and horizontally. So let's take this force. These are all either vertical or horizontal forces. The only one which isn't is this one here, which is T. So we're going to just decompose that into a vertical component and a horizontal component. My horizontal component there is going to be T cos 40, so that's 61 cos 40. And my vertical component is going to be 61 sine 40. When I'm using my calculator, I want to use my stored value so that I don't let any inaccuracies develop. Resolving horizontally, let's just resolve to the right. It tells me that the rightward component of the force at A must equal the leftward component force here, equals 61 cos 40. On my calculator, I'm just going to do that as A cos 40, which gives me an answer of 46.7 newtons. And I'm going to again just store that in B. If I resolve vertically, I've got the vertical component of the force plus the vertical component of my tension, plus 61 sine 40, must equal 6 times 9.8, and it gives me AV is equal to 6 times 9.8 minus A sine 40, and it gives me 19.6 newtons. Notice that what I want is the magnitude and direction of the force. I've got it in component form, so let's just do a triangle to show what that looks like. The vertical component of the force and the horizontal component of the force. So the horizontal component of the force is rightwards of 46.7 newtons, and the vertical component of the force is 19.6 newtons. So the magnitude of the force is just going to be 19.6 squared plus 46.7 squared, and I square root that to give me magnitude of the force, which is 51 newtons. The direction of the force, theta, is going to be inverse 10. Of my 19.6 divided by 46.7, just so that we can see it on the calculator, which is 22.8 or 23 degrees. And we need to just be really clear with the examiner to say 23 degrees above the horizontal, and away from the wall.